as Brandy was saying, I did my undergraduate degree at USA, and I actually got a double major in biology and geology. And while I was there, I spent 2 summers here taking classes as an undergraduate. And I got to say, it was probably one of the high points of my life. I see Brian over there. Lived on the dorms here, and it was just such a great experience, just being completely immersed in marine sciences. And I think, you know, I can attribute some of where I am today to being inspired by just diving into the science. So really nice to be back here. Really nice to see how things have changed and have really grown here since I was here almost, I guess, 18 years ago, which is kind of scary to think about. Okay, so brief, let me see here. I think I'm frozen or, there we go. I can use the mouse. So a brief kind of personal background. I want to give you a little bit of my perspective, and since I'm going to be talking about things that overlap with marine sciences, I think it's kind of important to bring kind of the terrestrial side of the equation. So Brandy mentioned I did my PhD at Clemson. I'm a groundwater hydrologist or hydrogeologist, however you want to call it. So my focus, my interest has always been in groundwater. When I was at Clemson, I worked with some very nasty groundwater we call produced water. This is water that comes up when we extract oil and natural gas. Did I?
We're not.
I'm still muted. It says.
It's actually screen sharing that is not happening. So I apologize.
No, it's no problem. Oh, I need to hit share screen. You can't see the slides.
Nope.
Should be
this one, correct. Thank you so much.
Okay. We're good. I guess for those that are online, I don't think you missed anything too important. So as far as pictures are concerned. So now I can't see my slides. Here we go. Okay, here we go. So produced waters. These are waters that are brought up during the production of oil and natural gas. So you may not realize, but when we produce oil at the surface, we get the petroleum, obviously, but we also get a lot of byproduct water. So for instance, for 1 barrel of oil, you might pull up 10, 20, even 50 gallons of water. And this water is geologically old water that's been in contact with petroleum for quite some time. So it tends to have a lot of nasty things in it we call constituents of concern. It presents kind of a treatment issue, a management issue for the production of oil and natural gas. So our role, I was funded by the Department of Energy there. Our project was to try to characterize some of these waters and see if we could do anything good with them, do beneficial use. So could we treat this water? Could we use it for agriculture, for instance? Could we use it for livestock watering? And to keep the costs low, we looked at passive treatment systems. So kind of focused on designing constructed wetland treatment systems, which are kind of like these artificial wetlands where we take advantage of natural biogeochemical reactions that can transfer and transform some of these constituents of concern. So spent 5 years up at Clemson. This is kind of like my outdoor lab on the right side there, designing different wetlands to remove metals and to remove organic compounds and to remove nutrients. So it was kind of a change to come back to my alma mater, to come back to USA and to the geology program that we have here. I definitely took a little bit different trajectory with my research because we are an undergraduate program. Having graduated from the geology program, I was really interested and very passionate about involving undergraduate students in my research and getting them the experience that they need to take things to the next level, whether that's a career or whether additional research comes with that. Just a little bit about our program. We're up on the main campus here. It's a smaller, like I said, undergraduate program. It's a great experience for the students, kind of building on this immersive experience. We do have a capstone field course, and that's the picture on the left there. That's up at the top of Wheeler Peak in New Mexico, so about 13,000 feet or so. We hike up at the end of our field camp, which is kind of like the pinnacle, you know, physically and also, I guess, figuratively as well. On the right side, that's part of our well field that we have on campus. So we have a number of groundwater wells installed. I teach hydrology courses and geophysics courses on campus where we focus a lot on groundwater hydrology, which is what I'm going to be talking about. So bringing my perspective as a groundwater hydrologist, you think about the hydrologic cycle. It's really kind of fascinating to study something that you have direct encounters with every single day. Like the other day, we had the rainstorm that came through. We had a tornado that passed not too far away from my house. So you can see definitely elements of the hydrologic cycle. You see clouds, you see precipitation, you see water running across the surface, discharge, you name it. Groundwater is kind of an interesting thing, and it's kind of interesting focusing on the subsurface because this is largely unseen. So, things are taking place underneath our feet. So a lot of times groundwater and groundwater transport within the hydrologic cycle isn't something that's on the top of your mind. It's not something that you're necessarily seeing. It's not right there in front of your face. So it kind of takes a little bit different approach to study what lies beneath the surface. On the terrestrial side of groundwater, I want to give you just a little crash course in some of the tools that we use. The way that we describe groundwater flow is based on a very famous equation, maybe one of the most widely used groundwater transport equations out there, called Darcy's Law. Darcy's Law basically describes flow as being a product of two different things. I apologize for so much math on this slide, but to break it down, I think you'll find some common formulas that share the same sort of setup. We'll just look at this lowercase q right here. This is for specific discharge. This is groundwater flux. So lowercase q would be the groundwater flux, and then we have negative k times delta h over delta L. K right here is what we call the hydraulic conductivity, and this describes the ease with which groundwater moves through the subsurface. So whether that's sediment or whether that's rock. So something like a sand would have a higher hydraulic conductivity than something like a clay. Water will drain through sand quicker than it will through clay. It will pass through quicker. So that's kind of the conductivity side of the equation. The thing that drives the actual flow is our potential energy field here, which is delta H over delta L. And this is just kind of another way of describing a pressure gradient. So the H would be the water elevation. So we're just looking at water flowing in the negative direction along that gradient from a higher elevation to a lower elevation. And we could convert those H values over to pressures. So this makes a lot of sense. Groundwater is flowing along a pressure gradient from a higher pressure to a lower pressure. So if you understand that, you probably understand about 50% of terrestrial hydrogeology, I guess. I said that there are some commonalities here. You probably have heard of a diffusion equation. We could replace hydraulic conductivity with diffusivity, for instance, and we could replace the pressure gradient with a concentration gradient, and we could describe diffusive flux. Dissolved solutes move from a high concentration to a low concentration. Same thing. We could also replace conductivity with electrical resistivity, which would be the inverse. And we could replace the pressure gradient with a voltage gradient. And then you're describing Ohm's law, which describes electrical current. So they're all the same equations. It's just here we're talking about groundwater flow. So moving on, another famous equation within hydrogeology here describes what happens when we take a terrestrial or freshwater aquifer and we get close to kind of the physical barrier with the sea. So this is a physical barrier. It's also kind of a discipline barrier between hydrology and between, I guess, marine sciences and oceanography. So where the freshwater meets the saltwater, in other words. So we have the Geibin-Herzberg relationship here. This is basically showing that freshwater is less dense than saltwater. So in the subsurface, freshwater actually floats on top of the saltwater. We have a freshwater-saltwater interface. And because the freshwater is less dense than the saltwater, we actually have a little bit of buoyancy that allows that freshwater to be suspended above mean sea level. So it's just very similar to the way that you would describe an iceberg floating, where a certain portion of the iceberg pops up above sea, and then you have a root of that iceberg that lies beneath the sea level that's providing the buoyancy force to keep that suspended part above the water. What's interesting about this equation and what's used a lot in hydrogeology is this relationship between H, which is the level of the water in the aquifer above sea level is the dashed line, and then Z, which is the depth of the water or the root of fresh water that's supporting this H value right here. So hydrogeologists a lot of times think about this relationship where Z tends to be, just assuming densities for saltwater and freshwater, Z tends to be about 40 times H. So in other words, for every 1 meter of H above sea level, you have about 40 meters of this freshwater route. And that comes into play when we start pumping water from coastal aquifers. So if we start producing water to the surface, as we do in Baldwin County and even here in Dauphin Island, then you get a cone of depression where the surface water level gets drawn down. If you draw the surface water down by 1 meter at the surface, then you could expect to see 40 meters of saltwater intrusion coming from the base, coming from that route. So hydrogeologists definitely concerned about saltwater intrusion from a water supply standpoint. But this is this Gibbon-Herzberg relationship right here kind of has a lot of assumptions that are definitely not valid. It's a isostatic sort of setup. It's steady state. It doesn't take into account changes in the freshwater. It doesn't take into account discharge. And so this is kind of where hydrogeology has kind of come to a stop, I guess, up until probably about 2 or 3 decades ago. We just kind of get to the ocean as far as groundwater is concerned. We get to that saline interface, and that's kind of the end of the terrestrial domain. And then we pass the torch, I guess, over to oceanographers, and we say, you know, you've got the oceans, you guys have this covered. So you have this kind of discipline barrier between the two. Up until fairly recently, there's been a lot of advances. So one of the things that we can change, thinking about this Gibbon-Herzberg relationship, one of the things that keeps it from being static, or some of the assumptions that we made that are not valid, is that we get precipitation that falls on the land surface. Precipitation will trickle down through the sediments in a process called infiltration and ultimately recharge the groundwater. So we add to that freshwater volume. If we do that, according to the Gibbon-Herzberg relationship, we would expect the water table elevation, the surface elevation of that water table to rise. So if we're rising the part above sea level, we also have to increase the thickness of the root that supports that. So we would expect this interface, in other words, to expand quite a bit with increasing recharge, and we're expanding this freshwater domain into saltwater. So that should cause some displacement and some discharge of saline water farther offshore, and this is something that's been described fairly recently. Along with the recharge, we would expect to see a little bit of lensing that takes place as we get closer to the shoreline, and some direct discharge of fresh groundwater. Again, something that's been fairly overlooked up until the last 2 or 3 decades. So that's kind of the terrestrial side of where the land meets the sea, but certainly there are a lot of things that happen out in the ocean, oceanographic processes that could play into this exchange of groundwater and surface water. Just a couple of them, you know, we think about sea level as being something, I guess, static from a hydrogeologic perspective, but certainly it's not. Sea level is changing constantly just due to tides. So if you think about this being a pressure gradient from groundwater flowing from a higher elevation to a lower elevation, and then you have this tidal pumping, you can see how those fluctuations due to tide could lead to exchange. Another thing is that we see changes in density of the surface water due to changes in temperature, changes in solute concentration. That should lead to density-driven convection right there, another way that we can exchange water between surface water and the groundwater. We also have waves that will lead to wave run-up, wave setup, and as those waves cross onto the land, we expect to see infiltration. Again, that can add to the recharge, and that water can drain back to the surface. And as I mentioned earlier, we see changes in this interface that will take place due to changes in the hydrologic head, the water table elevation on the surface. So this picture has kind of come together, again, fairly recently as far as science is concerned. And we have a little bit better understanding of what happens between the terrestrial side and the marine side. And we have this unique zone where we have several driving mechanisms for groundwater exchange with surface water. We have a lot of different reactions that can take place that can change the nature of the surface water and the incoming fresh groundwater as well. So actually, hydrogeologists did not come up with this term. This is actually a chemical oceanographer's definition, but it works quite well. So this is from Bill Burnett from Florida State. He defined this, this area, the water exchange to the surface, as submarine groundwater discharge, and that is the flow of water through continental and insular margins from the seabed to the coastal ocean, regardless of fluid composition or driving force. So that second part right there is kind of interesting to think, regardless of fluid composition or driving force. Hydrogeologists, we think about discharges as being some sort of net flow from one boundary to another boundary. Regardless of fluid composition, driving force introduces this recirculation that takes place due to tidal pumping, due to density-driven convection, due to wave run-up and wave setup into this broader term of submarine groundwater discharge. So I think early on, the first time I heard this definition, it was a little bit, I was a little bit skeptical, I guess, of this idea of including something that's just a recirculation process. But I think there's another definition that kind of plays the importance of this recirculation. We know this, we have an estuary right behind us, and we know we have fresh water from the land meeting salt water from the Gulf of Mexico. We have an estuary where we have mixing processes. We have retention times. We have all sorts of geochemical transformations that can take place that change the nature of the fresh water and change the nature of the surface water and produce something quite unique. So there is a term that we use to describe this subsurface estuary. We have what is known as the subterranean estuary, and this definition is very similar to at least one of the definitions of a surface counterpart estuary. So this is a zone where groundwater derived from the land, drainage measurably dilute seawater that has invaded the aquifer through a free connection to the sea, which I think if you replace the word groundwater, that's more or less the definition of an estuary, right? So my adventures in submarine groundwater discharge actually began kind of as an opportunistic development for me. I moved to Mobile, moved back to Mobile to work at South Alabama in 2013. And as I mentioned, I'd been working with produced waters. I'd been working with constructed wetland treatment system design. I was really looking to open opportunities that would serve our students, give them opportunities to do undergraduate research, and also kind of turn my attention to new projects that interested me. So I was very interested in groundwater interactions along our portion of the Gulf of Mexico. At the time when I started, 2013, we had really no studies of submarine groundwater discharge in Mobile Bay. So it provided a nice opportunity for me. So the first study that I did was actually a small kind of field study working with a single residence here. This is actually where I lived when I moved here. So this is kind of some backyard research. Again, opportunistic here. So the location of my first field site is right here. This is a small community called Alabama Port. It's right where Dolphin Island Parkway and Highway 188 come together right there. This is an area that I lived temporarily with my wife when we first moved here, and we were trying to get things settled. Fortunately, my parents, they have a house there, and they had a small shack that we could live in while we saved up money to purchase the house ultimately. Living on the shore of Mobile Bay throughout the year, you know, especially into the winter, gives you an exposure to the elements, lets you see things that you normally wouldn't see, lets you think about the way that water moves through the environment in a little bit different way than I do now, where I'm a little bit more sheltered. For one, this time of year is not the best to live close to the bay because it just stays wet all the time. We get rain, the ground saturates, it doesn't drain very well, so we're soggy all the time. You really want to stay off the grass. You can see that in some of these pictures over here. It just seems like it would never end. A little bit alarming about the fact that the land is almost always saturated during the cooler time of the year is that we're living out in a rural area. We're kind of far away from any sort of centralized wastewater treatment, and many of the houses still along Dolphin Island Parkway rely on on-site wastewater treatment to deal with, well, wastewater that's generated. So you will see as you drive up Dolphin Island Parkway on your way to Fowl River, if you're driving north, you will see most of the houses have some sort of mound in the yard, and that mound is not a geologic feature at all. These are raised mound infiltration systems to deal with on-site wastewater treatment and disposal. So people have septic tanks. In other words, the septic tanks will pump the effluent up into a raised mound where the water trickles down, presumably leading to degradation of the nasty things in the septic effluent, or so one would hope. So this was kind of interesting to me, having this saturated yard, having on-site wastewater treatment, being so close to the shore of Mobile Bay that I decided why not take a look at it. So here is the property looking back towards the land. So from the pier, in case you're wondering, this is not the house that we lived in, unfortunately. It's reserved for the parents there. But this is actually an interesting place to take students and show them surface and groundwater interactions, because you can just look, you can see the groundwater. I can highlight this on the bulkhead here. You can kind of see this boundary between saturated boards and unsaturated boards. If I zoom in a little bit closer, this is not the high tide mark. It would be a bad thing if that was the high tide mark, because it's pretty close to the land. This is actually the level of saturation. This is the water table that we're seeing right here. So a good illustration of, saturated conditions, a water table elevation that is higher than the elevation of the top of Mobile Bay leads to that pressure gradient, which leads to submarine groundwater discharge and flow from the land surface towards the bay. So I did what any other curious scientist, I think, would do. In my case, hydrogeology, I started punching holes in the ground. I started digging wells, installed 6 wells into the backyard there. It's kind of one of those things where it's easier to beg for forgiveness than ask for permission, but there they are, the wells installed, jetted some down, drilled some down as well. And these wells provide places where we can measure the water table elevation, get an understanding of that pressure gradient. We can actually test the hydraulic conductivity of that superficial aquifer there and get an understanding of at least some of the components that we need to use Darcy's law and predict groundwater velocities. So the wells were installed, they were surveyed in, so we have a good comparison between elevation of the water table in each one of those wells compared to sea level. We also had a weather station installed there that was just an extra constraint for us, so we get an understanding of how much precipitation and evapotranspiration is taking place on site and do kind of a rough water budget, a water balance. So these maps right here show us the water table elevation. These are very similar to topographic maps, except instead of showing the land surface elevation, these are the water table elevations. Just to kind of get you going, because I'll show you a couple more of these maps. The left side here, this is the land. So moving to the west, that would be further inland. The right side, this dotted line right here, that's the seawall. And so basically east of that seawall, that's Mobile Bay right there. That's the shoreline. So the darker blue colors, those are higher elevations. The lighter colors, those are lower elevations. And this is a great example of that pressure gradient right there. Groundwater flows from the higher elevation to the lower elevation. I've added some vectors on top. These arrows right here are perpendicular to the contour lines. They show the direction of groundwater flow, and also the length of these arrows scales with the strength of that gradient or the slope of the water table. So the longer the lines, the higher the rate of groundwater flow. I don't have dates on these, but this is January in the top left, March, and then sometime in the summer, I think it's July, and then October. So basically following 4 seasons of a calendar year right here. It's subtle. You can kind of see that there is higher water table elevations generally in the wet, cooler season, so January, March, and then things kind of dry out as you make your way through the summer and the fall, which is certainly a regional trend here for the most part. There are exceptions to the rules. So we get higher flow in the winter, basically lower flow as we move into the summer. This makes sense. Again, the regional trend for us here is that we get precipitation regularly in Mobile and Mobile County and Dauphin Island, certainly. We get rain basically all the time. But what does change from a water balance consideration is that evapotranspiration is not constant. We get a peak of evaporation from the land surface and plant transpiration in the summer when we have long photo periods, long days. In other words, the plants are growing. They will absorb a lot of that moisture and send it to the atmosphere. In the winter, when days are shorter, when plants go dormant, we have less evapotranspiration. That's what's allowing this water to build up during the, quote, wet season for us. So these wells provide an opportunity for us to determine the directionality of flow, to calculate freshwater loadings in terms of submarine groundwater discharge. But they also, ultimately, this was our goal from the get-go, is they provide places to collect groundwater samples and to see if there was any influence from this raised mound infiltration system. So again, these maps are similar to the maps that I showed earlier. The very top left right there, we have W3 in each one of these maps. This is about 10 meters east of the raised mound. So the raised mound would be basically just off the map right there. So I have a transect of 3 wells kind of along the direction of flow downstream of the raised mound. And then I have 3 wells on the south side of these maps that are not down gradient of a raised mound infiltration system. What was a little surprising, I guess, and that's why we do this, right, is I didn't see a whole lot of influence from the septic effluent. There was a little increase in total nitrogen, a small increase in biochemical oxygen demand, a small dip in dissolved oxygen concentration, and just a little bit of elevated, I guess, salinity here, the electrical conductivity of the water. So I was expecting to see more, honestly, but it turns out there wasn't much of an influence. I think there's possibly an explanation that we just get so much rain that likely the effluent is diluted to a certain extent. But nevertheless, that kind of shows, you know, what's happening from the terrestrial side. And this is where things get a little bit more interesting. Moving into the marine side, trying to see what happens to the water that's actually coming out of the surface. Does it match what we're seeing on the terrestrial side? So I got the students involved in this research. First wanted to see if we could find a zone where this fresh water from the land is discharging to the surface water. So got the students equipped with some sondes, let them paddle around a couple times and put together just some simple salinity maps. These maps show the shoreline is on the west side, and then moving further to the east, that's making your way in your offshore direction. There's a little bit of freshening, and this happens consistently. The 4 times that we've done this, we see some freshening of the surface water that shows up usually within about 50 to 100 meters of the shoreline or so. So the next step for us then was to make some direct measurements of submarine groundwater discharge. One of the instruments that we use is called a seepage meter. I think some people may call this a benthic flux meter. I think there's a couple different names for them. It's a very simple piece of equipment. It's just basically a 50-gallon drum where the bottom 2/3 of it are cut off, and we attach a hose in a collection bag. We drive these things into the sediment. We let them absorb submarine groundwater discharge or collect submarine groundwater discharge, and we measure changes in volume of some pre-attached bags. I don't think I'll be using seepage meters again. These are quite labor intensive. So you have to make sure that you're out there checking the bags regularly. You want to run them across an entire tidal cycle to take, you know, into account changes in surface water elevation. You have to make sure the bags are pre-filled with a certain amount of water so you can have negative submarine groundwater discharge. You can actually have water from the bag flow back down into the ground for recharge processes. Don't want to get them too full. So did this seasonal study. Every 4 hours we'd go out and change the bags. Unfortunately, nobody wanted to join me in the winter season. So in January, unfortunately, I don't have any pictures of undergraduate students working with me. I'd go out there at 4 in the morning to change out some seepage meter bags in January. It was kind of interesting. So here's what we get from the seepage meters. This is kind of an overview of one of our sampling periods. The tide stage right here is in this darker blue, and then the different colors that you see on the top graph represent different distances from shore for the seepage meters. So the majority of the flow that we collected with our seepage meters happens quite close to the shore, within about 12.5 meters. And then we get a decrease in flow the further offshore you go, which is kind of what we expect from the Guyton-Herzberg relationship and from other studies, certainly. As far as time is concerned, there is this kind of tidal pumping that appears. During high tide, we see a decrease in flow, and then during low tide, there's an increase in flow. So that makes a lot of sense from this pressure gradient standpoint. At low tide, you have the highest gradient. That's when you expect the most flow. During high tide, the gradient is lower, so you expect lower flow. One of the things that really stood out, though, when we started using these seepage meters is that the rate of discharge, when we integrate across the shoreline here, is about 3 cubic meters per day per meter of shoreline. That's about, I think that's about 10 times higher than what we were predicting based on the terrestrial hydrologic gradient. So based on what the wells were telling us from a water flow standpoint. So in other words, we're getting a lot more flow coming out of the sediments than we're getting from the land. So certainly points towards some sort of recirculation process. So to dive into that a little bit further, we did take another technique we borrowed from chemical oceanography. We use a set of electronic radon detectors that we towed across the shoreline here. These are able to monitor radon in real time. There's a water-air exchange chamber, which you can see in the front here. We just basically are pumping water, spraying it through this exchange chamber, pumping the air in a closed loop to our electronic radon detectors, which are safely stowed inside of this box right here. Radon is an excellent geochemical tracer for groundwater. When you think about radon, you might think about somebody with a basement and radon collecting. It's because radon is generated during radiometric decay of radium-226. So things that are in contact with soils, things that are in contact with the ground will accumulate radon. Radon breaks down, or it decays relatively quickly. It has a half-life of just under 4 days, so it doesn't hang around very long. So groundwater is exposed to the sediments, it's surrounded by sediments, it's surrounded by sources of radon, so it tends to be elevated in concentration of radon relative to surface waters. So in other words, we're basically sniffing the surface water for radon. If we see radon in the surface water, it's a pretty good indicator that we have a source of groundwater nearby. So we can actually do a mass balance on the radon as well, and we consider what happens to the radon in the surface water. A portion of it's going to decay due to radiometric decay, a portion of it's going to mix with offshore waters, a portion of it's going to volatilize the atmosphere, and a portion of it's going to be diluted by mixing with surface waters. The only unknown in our mass balance is the flux of radon, which we can use then if we determine the flux of radon and we know the concentration or the activity of radon in the groundwater, that we can actually use this to calculate a submarine groundwater discharge rate, or we can determine a flux as well. So putting the whole story together, we have some measurements of groundwater flow from the land side, from the terrestrial side, some measurements of groundwater flow down, the seepage meters and the radon from the marine side of things, from the offshore side of things. And there's actually quite a difference here. So these top three numbers right here, these are coming from measurements of fresh submarine groundwater discharge. So our hydrologic balance from our weather station, Darcy's law, that's using the wells, and radon inventory using a terrestrial aquifer end member. We're falling somewhere between 0.2 and 0.5 cubic meters per day per meter shoreline. When you compare that with what we're actually measuring out in the bay, those numbers are about an order of magnitude lower. So there's quite a bit more discharge, 3.2, 4.7 cubic meters per day per meter shoreline measured with the seepage meter and radon inventory respectively. So definitely points to some sort of recirculation mechanism is the dominant form of submarine groundwater discharge, at least at our site. This becomes really interesting when you consider the nutrient concentrations in the pore water and in the surface water, the terrestrial groundwater. We can actually calculate nutrient loadings, and the nutrient loadings for the marine side of things, so these are based on samples we collected from our seepage meters, are almost 2 orders of magnitude higher than what we're predicting nutrient loadings from the land, so from what our wells are telling us. So there's a much larger loading of nutrients coming out of the seafloor sediments than we can explain as being derived from the land. So obviously something is going on here. Total submarine groundwater discharge, so this would include recirculated seawater and what's coming from the land, is much higher than just the fresh submarine groundwater discharge. The loading is much higher into Mobile Bay than we would expect by just looking at the wells. So our explanation for this was just, there's got to be some sort of recirculation mechanism that would explain the flow. And from the nutrient side of things, there's got to be some sort of recycling that takes place, some sort of change that probably takes place within the subterranean estuary. So this being kind of my first adventure into the marine side of groundwater, submarine groundwater discharge, was a little interested to put this paper together and see what the peer reviewers thought. So we actually published this. I published it with an undergraduate student who was very helpful in analyzing these samples and writing the manuscript, and it got published. And we were a little bit, anxious to see what others would say if there was going to be some sort of follow-up study. And there's actually been a number of studies since our study came out. Many of these coming from Natasha Demova's lab up at the University of Alabama. Her graduate student, Daniel Montiel, did an excellent job, a much more exhaustive study. They looked at the Mobile, they looked all the way around Mobile Bay and more or less found similar conclusions that the nutrients that come from groundwater that enter Mobile Bay are more than likely coming from natural sources. They attribute those nutrient fluxes to a subsurface layer of organic material that they found. They call it a peat layer. So it's kind of an interesting thing, kind of a change in perspective looking at the terrestrial side of things would predict much lower nutrient concentrations. If you were looking at just the marine side of things, just what the seepage meters are telling you, you see this large flux, this large nutrient loading. You may want to directly attribute that to what's happening on the land with the septic systems, but it turns out it's kind of a combination of the two. The septic is not really all that important in this case for the nutrients that we see coming out, and the freshwater side of things isn't fully explaining things. It seems to be that there's this recirculation mechanism that's taking place that's releasing these nutrients, maybe recycling, maybe some sort of remineralization that's taking place. So since then, I've moved on to, I guess, a different water body to study submarine groundwater discharge. I've been spending a lot of time lately over in Little Lagoon. So this is over in Gulf Shores, kind of on the east side of the Fort Morgan Spit right there. This is an excellent place to study submarine groundwater discharge because there's been a lot of background research in this area. It's considered a groundwater dominated lagoon. So there's no major streams or rivers that flow into it, unlike Mobile Bay. So the fresh water that enters into the estuary there is mostly derived from groundwater. There's been a number of studies in this area. I'm sure some of you guys I was talking to somebody earlier about Justin Leifer. Hugh McIntyre originally identified a hotspot of harmful algal blooms associated with submarine groundwater discharge over at the mouth of Little Lagoon. And they actually were able to correlate those harmful algal blooms with peaks in discharge of Styx River, which is kind of interesting because Styx River is a good proxy for groundwater discharge because it's in the same aquifer system. So when Styx River is flowing heavily, we expect that groundwater in the whole aquifer system has a higher flux, and that's then something that's correlated to these harmful algal blooms. I was originally drawn to Little Lagoon working with a colleague of mine, a coastal engineer. Some of you may know Brett Webb. He's on campus at USA, and he actually still is studying the stabilized inlet right here, which has some issues with infilling of sediment. So he had a master's student working on a hydrodynamic sediment transport model that showed that groundwater flux was actually changing the hydrodynamics of that pass and allowing for increased infilling of sediment. So he brought me on board to look at the groundwater situation in Little Lagoon. So walking into this area, I immediately started to, having done a study already, I was really kind of interested in seeing what's happening in the subsurface, seeing what's happening within the subterranean estuary. One of the things that we've been doing recently is we've been installing or deploying these things. It's actually a technique I picked up at Clemson called a light oil Piezomanometer. And it's a pretty simple piece of equipment. On one side, we have a piezometer. This is basically just a very thin well. In this case, it's a stainless steel rod that has a piece of tubing that slides down through the middle of it. And then the tubing is slotted, and so we can extract groundwater samples with it. So we can drive this thing down, we pull it up a little bit, and we can pull water samples into it. What's interesting about the piezomanometer is on the other side, we have a manometric loop. So this is just a loop that's sealed at the top. One side of the loop is connected to the piezometer. The other side of the loop is open to the surface water. And we use oil as the interface above the water right there. It provides a nice density contrast. It's a lot like the Geiben-Herzberg principle. Using that oil kind of magnifies the difference in pressure between the subsurface, the piezometer, and the surface water, which is the other open end of the manometer right there. So you can think of this as basically being like a voltage meter, where you have a positive side, a red electrode, and a black side, and you basically stick it between 2 points, and you can determine the potential between the two. So in this side, the piezometer is dropped down into the sediment. We can stop it at different intervals. we have the other side open to the surface water, and we can measure the potential, the pressure gradient between the subsurface and the surface waters. So we can put together a nice image here. So this is just the first time we deployed the Piezomanometer. This is kind of like what I was showing you earlier with the water table elevation maps, just this is flipped onto its side. So we're looking in cross-section at the subterranean estuary. This left side right here is the shoreline, and then moving offshore towards the right, the dotted line, or the dashed line rather, that you see right there is the seafloor. So there's a pretty good pressure gradient here along the shoreline, and then that pressure gradient rapidly decreases as you reach the surface water. So within about the first 5 meters of the shoreline, that's where we're seeing these vectors again are showing the direction of flow. The length of them is showing the strength of the gradient. So presumably this is the rate of discharge or the flux of groundwater. So most of it is taking place close to the shore. What's interesting is as you go further offshore, this gradient is actually reversed. So all the way over here on the right side, about 12 meters offshore, the pressure of the groundwater is actually lower than the surface water. So the gradient then dictates that surface water is being drawn down into the sediments there. So a pretty good illustration of more than likely we have mostly terrestrial groundwater flowing up towards the surface, and it's more than likely that as this water is advecting towards the surface, we get a little bit of a convection cell that's taking place over here on the right side. Unfortunately, we encounter something in the subsurface that we're not able to penetrate. I think more than likely we're looking at some sort of redox change that's precipitating some minerals that are holding that sediment together. So we haven't been able to penetrate that side with this set of figures. We can also use the piezometer to take pore water samples, so we can look at what's moving in the subsurface. So this is showing us total dissolved nitrogen right here. You can see the area that had the most flow associated with it, the highest pressure. So the area or the water in the subsurface that's in motion is elevated in dissolved nitrogen. Of that dissolved nitrogen, a good portion of it is in a reduced form. So this is ammonia right here. So there's a plume of ammonia associated with that flowing groundwater. Not so much nitrate. So again, this is mostly reduced forms of nitrogen. And then we look at the salinity of the water over here. This plume is actually brackish in its composition. It's fresher than the surface water, but it is not the surface water actually is not the saltiest water. We see actually some of the groundwater in the subterranean estuary is actually saltier at times than the surface water, which is kind of interesting. So this shows us a nice plume of nitrogen water coming from the land and making its way towards the surface. And we now have the pressure data showing that this is indeed moving towards the surface. So moving backwards, again, trying to track down where are these nutrients coming from, where's the nitrogen coming from. I've been working on a project as part of a watershed management plan for Gulf Shores. This is something the National Estuary Program has funded, where we've been looking at terrestrial sources of nitrogen around the lagoon. So around the perimeter, I have a number of places where I've sampled groundwater. These include wells that we've installed ourselves. So again, getting the undergraduate students involved, we found a number of landowners that actually were welcoming of us to go onto their land and install small, shallow groundwater wells. There's a number of irrigation wells in the area that we can sample, and there's also some groundwater seeps in the area that we can sample. So we've been looking at what the terrestrial component of the groundwater has in terms of nutrients. Really, we're not seeing a whole lot of nitrogen in the groundwater, the terrestrial groundwater, except in a few isolated areas. On this map, the top one shows us just total nitrogen. The size of these bubbles scales with the concentration, and the color becomes more red at higher concentrations. So we have this kind of elevated hotspot right here, higher nitrogen concentrations, and then some more over here in the southeast portion of the lagoon. Phosphate, similar story, except the hotspot seems to be right here, just north of the pass. Not so high concentrations than the other wells that we're looking at. What's kind of interesting about this to me is that, you know, as part of this study, we're looking at different sources of nutrients in the groundwater surrounding Little Lagoon. And as it turns out, just over here, this hotspot is located, there's actually a wastewater treatment plant, there's a facility right there that instead of discharging the treated effluent to the surface, they actually have these large ponds that they discharge the wastewater effluent into, and from those ponds, the water infiltrates down directly into the groundwater. So they call it a disposal or a subsurface injection or disposal. That's what their permit is for, but it's really just seeping down into the groundwater. The jury is still out though as to whether the wastewater treatment effluent is responsible for these hotspots. I have some samples that I've sent for stable isotope analysis. Nitrate is kind of a mixed bag for us right now. Most of the nitrogen that we're seeing is in a reduced form. It's ammonia or dissolved organic nitrogen. So the nitrate isn't something that explains it for us all that well. I have some TDN digests that are actually at UC Davis right now getting analyzed, and hopefully that will provide a little bit more insight. So stay tuned there. Okay, on the other side, the flow here. So talk about the nutrients, talk about the flow. There are a couple of wells that I've actually been monitoring for some time, monitoring the water level elevation. So this actually is the first thing I did when I started working with Brett Webb. We installed pressure transducers in these wells. They've been running for almost 3 or 4 years now, collecting groundwater elevation data every 30 minutes. So have quite a long time series of groundwater elevation data to look at and to compare with kind of the meteorological parameters. So precipitation measurements, wind measurements. This is a view of the hydrographs from those wells, just to help your eyes a little bit. The two colored lines right here, TW5 and TW6, these are located a little bit further from the shore. TW1 is located very close to the shore, so about 5 meters away from the shore. This is a hydrograph showing the basically the water table elevation. It's the normalized hydraulic head, and then up here going down from the top, we have precipitation depth. So this is a hyetograph up on the top. Groundwater levels respond as you would expect to precipitation events. We get this nice surge in groundwater elevation, and then we get this regular decline. Almost looks like a surface water hydrograph. So precipitation events are leading to a groundwater recharge event, and then this decline is when we have submarine groundwater discharge. One of the things that stood out to us though, we're looking at this, is the black line does not always follow what the red and green lines are doing. For instance, it has this kind of 24-hour cycling in it, pretty good indication of some tidal pumping in that well. But also I've kind of highlighted some areas in blue right here and in orange over here where things are quite a bit different. I'll start with the orange area. This is actually a very large fluctuation in water table elevation within that well that we associated with the passing of Hurricane Barry. So Barry didn't make impact with us. It actually hit over in Louisiana. But one of the interesting things is we got a little bit of a storm surge here. We had south winds for a couple days. The blue and red lines right here are showing us the subtidal anomalies for Dauphin Island and Pensacola. You see that surge showing up in tidal gauge data, and the surge also shows up in groundwater data. So this is showing us that we have some sort of wind mechanism that can lead to groundwater surface water exchange or submarine groundwater discharge. It's to be expected that storm surge would allow some circulation of water in the subsurface. But where things get interesting to me is we see this same sort of exchange take place during the passing of cold fronts. In fact, cold fronts provide ideal opportunities for this exchange because when the fronts move through in our area, we tend to get 2 to 3 days of strong south winds as the fronts are approaching and we have low pressure. We get a little bit of a surge. When the front passes through, we get strong north winds that blow the water offshore, and we see the opposite of a surge. We see a flushing event. That flushing event actually translates into the aquifer as well. So we have this kind of longer term mixing that's taking place. So we put together this image. These arrows right here are showing us the wind vector, so the direction of flow. So if we just focus on this in the middle, the F star, this was actually I call it a dry cold front because it did not rain. In the days kind of preceding this front right here, we have some south wind, so blowing towards the north, so we call that south wind. And then as soon as the front passes through, we get strong north winds, we get that flushing event, and you can see how the water responds. As the wind is coming, or as the front is coming, the water level rises. As soon as the front passes, water level drops off again. And these are groundwater levels. So this is something I've observed quite a bit where I'm living now. Pre-front surge and then a post-front flush, it translates into the groundwater. This is kind of unique because this phenomenon is a seasonal thing. Cold fronts don't happen all year round. We tend to see them pick up in November, and then they start to kind of slow down in April or so. So you have this kind of seasonal submarine groundwater discharge mechanism that can really start moving large volumes of submarine groundwater towards the surface. So looking back at Leifer's paper in 2009, where we talk about a hot spot of algal blooms in Little Lagoon, those blooms tend to show up at the same times when we have the passing of fronts and when water temperatures are warm enough to support harmful algal blooms. So I have some suspicion that these harmful algal blooms could be triggered by the passing of these fronts. These large flushing events of groundwater, these nutrient-rich groundwater comes to the surface after a front when we have clear skies, we have sun, we have warmer temperatures. This time of year, we really have the ingredients to kick off the bloom. Just actually submitted this earlier this fall, and actually the manuscript describing this mechanism was just published a couple days ago. Again, very happy. One of my co-authors, Mary Brandon Hutteman, she is an undergraduate that was working in my lab on this project. So I'm kind of excited to keep moving this forward into the future. So just as an end here, looking in the future direction, backyard research. I've had a radon monitor in my backyard for 2 years now. My wife has been very patient with me. I've been monitoring radon activity, and here we go again. This is showing surface water temperature in purple, radon activity in blue. Here's a cold front that moved through, and then a nice spike in radon. So definitely hope to expand this into Mobile Bay, the river systems that we have, because I think there's a lot of interesting things that can take place due to this flushing event. So I think I've probably exhausted my time. If there are any questions, I'd be happy to take any that you may have. Yeah, hey, Brian.
Good talk. Do you
Thank
have
you.
a feel for the relative input of nutrients from the groundwater discharge versus surface water runoff? And thinking about the phenomenon of Gulf Shores North Beach, Hydrographs.
Right. So the question was, do I have kind of a prediction of the comparison of loading between groundwater and surface water? They're actually in the paper that Daniel Montiel has for Mobile Bay. There actually are some comparisons in it. The groundwater is not as important during certain times of the year in Mobile Bay, just because we have so much of a larger catchment that's bringing water in through the river system. But as you move to Little Lagoon, then it's more than likely you're getting a much higher contribution from the groundwater. In fact, again, it's a groundwater dominated system, so it's one of the primary drivers of nutrient supply to that water body. What happens further offshore as you make your way to like the Gulf frontal beaches, I'm not entirely sure, but I suspect that you probably fall somewhere in between those two extremes. Thank you. Yes, question, Josh.
Yeah, I'm curious about the factoring in the impervious surface in your discharge measurements as far as like concentrating point sources of nutrient loading in those directions.
Yeah, so the question was if I've taken into account impervious surface as far as nutrient sources and groundwater flow are concerned.
Pretty much, yeah, like where you would have a lot of impervious surface that would concentrate a lot of point sources into a certain area.
Great, yeah. So impervious surface is being an area of concentration for nutrients. That was kind of one of the experimental considerations for where we were sampling in Little Lagoon. Let me go back to just the places where we collected samples. So the idea is that we would sample along a gradient of land uses. So the east side of Little Lagoon is where you have a lot of your impervious surface. It's a lot of commercial development in that area. As you make your way west, it turns into more residential development. And then of course we have the wastewater treatment plant. There's a golf course making your way further west. The kind of end member, I guess the kind of reference area is actually, if you make your way over to the far west side of Little Lagoon, it's the Bon Secours National Wildlife Refuge right there. So there's really no development over there. So yeah, it is taken into account. I haven't started picking out just land use cover data. And I'm still working on the interpretation right now. This is still a study that's in the works, but thank you. Yes, Ruth.
Back in Justin's initial work, it's really interesting. We didn't use isotope profiles. We did sediment and water isotope profiles. And I think if I remember correctly, we also identified those two hotspots that we found. But I actually don't remember talking about the wastewater treatment plant. So my question is, do you know how long the wastewater treatment plant has been there? And you may have said this, and I missed it. Do you know the transit time for the water from those pools to actually make it out to the sea?
Okay, so the question was about the wastewater treatment plant. How long has it been doing subsurface disposal for their effluent, and also how long potentially does it take for the water to move from those disposal ponds to Little Lagoon? To answer your first question, I believe that it's not entirely clear to me how long the disposal has been happening from a permitted standpoint. Their permit, I think, goes back to 2014. So Leafer's work precedes that. So it may have been, I don't really know the full history of the wastewater treatment plant. I don't know if they had a pipe that was going to Oyster Bay or somewhere else prior to the permit. As far as transit time is concerned, I've done just a back of the envelope calculation using the surface water elevation in the ponds and the surface water elevation of Little Lagoon, hydraulic connectivity. So basically Darcy's law. It's moving, the groundwater there is moving on the order of a few centimeters per day. So you're looking at on the order of hundreds of days to travel between the ponds and Little Lagoon.
The reason why I bring that up is so we did similar work on Cape Cod, and we found that it would take anywhere from 4 to 10 years
Yes.
for the groundwater to make it really show that it was covered.
Yeah. Yeah.
Almost always nitrate heavy and isotope active.
Mm-hmm.
But I was wondering if it'd be super helpful if you have the isotope ratios of the source.
Yes.
From the pond, if you did that, because I'm wondering if it would be sharing that up and you'd actually be getting less nitrate and more ammonia and actually lighter isotope ratios.
Yeah. Yeah. So the question was, I guess, an expansion on the transit times, and different locations tend to be much longer, and it would be interesting to have source isotope composition for the treated effluent. And I agree, I totally agree. What makes this a little bit tricky is that, so this is just a topographic map, a digital elevation model, I guess. The red line right there is the watershed boundary, so topographically defined, but it's a groundwater dominated system, so you don't really have surface drainage features. But groundwater tends to mimic the flow patterns on the surface. You tend to get kind of a repressed representation of the digital elevation model for the water table surface elevation. So in other words, the groundwater divide should follow the surface watershed boundaries. And the wastewater treatment plant is actually located like right on the boundary. So it's kind of unclear to me as to how much of it is flowing south towards the lagoon, how much of it is flowing north towards Oyster Bay. And the interpretation gets a little bit more complex because they are discharging water, which will cause regional mounding of the water table. And again, water flows from a higher elevation to a lower elevation. So there could be radial flow from those disposal ponds. So it's kind of an interesting thing to see. But yeah, we should talk more about the isotopes. I think it'd be interesting. Any other questions? I don't know if I looked online. No questions online? Okay, well, thank you guys very much. I appreciate your time.